Hi everyone, welcome to Organic Insight. In this particular video, I am going to discuss SN1 reaction, that is substitution nucleophilic unimolecular reaction. Directly, I will start with the reaction. In example, I am taking tertiary butyl bromide as a reactant. This is tertiary butyl bromide, which reacts with two molecules of water to give tertiary butyl alcohol. This is tertiary butyl alcohol plus this is hydronium ion and bromide ion it will give like this. This is the actual reaction. Then I will start with the mechanism of the SN1 reaction. Mechanism is very important in whatever the reaction is there. We have to understand the mechanism because the basics is there in mechanism. That's why I will start with a first step, which is what we have taken is tertiary butyl bromide. Here, okay, here I will write it as CH3. Here also CH3, CH3 is there. Now, in the first step, what will happen is this carbon and bromine linkage is there. This one will break heterolytically. That means this both the electron is there. It will taken by the bromine atom, and it is leave as bromide ion, and this is the slowest step of the reaction. I will show by reversible reaction like this. Now I will get a intermediate, that is tertiary carbocation, tertiary butyl carbocation, which is like this, plus, and here bromide ion. It is a leaving group here, leaving group, correct. This is carbocation. In the second step, what will happen is, now here I am taking tertiary carbocation is there, here CH3, here also CH3 and CH3 is there. In the second step, water is acting as a nucleophile. In the mechanism, we have to show each and every lone pairs like this. Water molecule in oxygen, it is having two lone pairs. One lone pair will attack this carbocation, which is forming here CH3 as it is there like this, and here I will get carbon attached to this oxygen, and here it is attached to two hydrogen atoms. One lone pair is there as it is. I am writing the oxygen is giving one lone pair, it is losing electron, that's why it will get a positive charge like this. In the next step, what will happen is, in the third step, this molecule is called as oxonium ion, you can call, or protonated tertiary butyl alcohol. As an intermediate, we generally will call as oxonium ion or hydronium ion like that. Here I am writing the same molecule like this. Here hydrogen is there, one lone pair and one positive charge is there, right? Like this. Now what will happen? The positive charge on the oxygen is second most electronegative element. That's why the positive charge on oxygen is very unstable. This bond is there, oxygen and hydrogen, it will withdraw two electrons like this, and it will be done by another water molecule like this. Water molecule is there, it will abstract the proton, and this electron it will move towards oxygen like this. Then it will give carbon and this 3-methyl group as it is there like that, CH3 and CH3, and here I am writing oxygen and hydrogen. This positive charge will get nullified and we will get two lone pairs looking like this, plus we will get oxygen which is attached, this one I am showing like this, attached to three other hydrogen which is having one lone pair and one positive charge. Generally we will write it as H3O plus, protonated water, like this. We can write this one as well. As a product we are getting tertiary butyl. This is tertiary butyl alcohol, right? Then we'll move on to the next thing, which is the rate equation. Rate equation. I hope the mechanism is clearly understood. Now, what is the use of this rate equation? What is the need for the rate equation? In the SN1 reaction, as an example over here, I am taking a two reactants, that is the tertiary butyl bromide as well as the water, which is acting as a nucleophile. This is nucleophile and this is tertiary butyl bromide, right? Then suppose if I want, suppose I'm getting a 40% yield when we conduct this experiment in lab. Suppose 40% is very less actually. I want to increase this percentage to something like 80%, 90% like that. I want a good yield of this tertiary butyl alcohol. Then we will start with different concentration. Suppose if I take this tertiary butyl bromide in more quantity, then we will check the whatever the yield we are getting, which is increasing or decreasing like that. Then again we will check with the nucleophile. When they checked with the both the thing, they came to one observation that when the rate of a reaction is direct or it is directly proportional to the concentration of tertiary butyl bromide only, but not on the concentration of nucleophile. Here I am taking a water as a nucleophile. Now how I can explain this? That means when we draw a graph something like this, here on the y-axis I am taking a rate of a reaction, and here I am taking tertiary butyl bromide. I can write like this. The square bracket indicates the concentration, and on the other side I will take here rate of a reaction as it is there like this, and here I will write a concentration of NaOH. I will take sodium hydroxide or water, anything, means one nucleophile, concentration of nucleophile. When we observe this thing in lab, we came to know that it directly depends on the concentration of tertiary butyl bromide. We will get a slope like this. We will get a straight line which is passing through origin. That means the rate equation is directly depend on the concentration of tertiary butyl bromide. Now, when we observe by changing the concentration of NaOH or nucleophile, we are getting straight line which look like this. This means the rate, how much ever the concentration we are changing about the nucleophile, but the rate equation is not increasing, rather it kept constant like this. That means a rate equation in SN1 reaction, in SN1 is independent of is independent of nucleophile used. This is the conclusion we got from this. Now, okay, now on the which basis it depends, on what basis the SN1 reaction is dependent. If I ask now, the SN1 reaction, it depends on SN1 reaction depends on the first thing is carbon skeleton. Carbon skeleton or structure, the structure of the reactant, and the second one is leaving group. Leaving group. We saw that in this reaction we will get a tertiary carbocation or simply carbocation as a intermediate. That's why we will get a carbocation as intermediate. If intermediate is going to be stable, then we will get a good yield, correct? If a okay, I will show in rate equation. Rate equation depends on the slowest step, that is what is the formation in the equation. Rate equation leads to formation of carbocation. If this formation of carbocation is there, if this one is good, if it is going very fast, then we will get a good yield also. That means the carbocation has to be more stable compared to other less stable. And if we know about how the stability will be there, we will get a stable like tertiary carbocation will be more stable than, this is tertiary butyl carbocation is more stable compared to secondary. Just I will write it as MeCH3 group, and here hydrogen is there. This is more stable. Tertiary butyl carbocation is more stable compared to secondary. In turn, this is more stable compared to primary, which is something like this. If a carbon is having a positive charge, it should have a 3 bonds around this, which is more than least is simply the methyl carbocation like this. This is the least stable. I will discuss the how the stability, what is the reason for this stability of tertiary butyl radical. And the second one, what we are telling is the SN1 reaction depends on leaving group, right? Leaving group. Suppose here I am taking something group, it is attached like this, and here I am taking as X. I will write it as CH3 only. Now here X can be anything. Suppose if halogens, if it comes, it can be fluorine, chlorine, bromine or iodine. In this one, if we add iodine, what is the rate equation, and what is if we add fluorine, how the reaction is going to change, which is the best leaving group here? We know that iodine is going to be the best leaving group, than bromine, than chlorine, than fluorine, because the pKa of iodine is pKa. This is very important to know, almost equal to -10, correct? Then that means HI is going to be very acidic in nature. If it is acidic in nature, this I minus will form very easily. That means it is very stable. That's why if we add, suppose here iodine like this. Suppose if we add iodine, it can leave with this electrons to form I minus very easily. It will form very easily. But this fluorine, if it is attached, it is very difficult to break. In organic chemistry, we will tell like carbon and fluorine bond is there, it is a dead bond like that, because this will not break easily. Now if we compare, okay, more leaving group compared to this, if it is there, yes, it is there, like tosylite group, you might observe this, and brosylite is there. Then azides is there. Suppose it is N3 like this, or N2. This is like this, N2 plus we can tell. Then like this, so many group is there. This is super living group. Based on this, we can tell the stability and the living group ability of a like living group. Now, I will I will start with energy profile diagram. Now, the energy profile diagram for SN1 reaction, it will look like something like this. Here is the reactants. This is the reactants. When we react with, suppose, if we will get an intermediate over here, and then again it will gives to product. Here we can observe two transition state is there, that is transition 1, this is transition state 2. What will happen in this transition state 1? Here we can observe that the carbon and bromine link, whatever it is there, it is going to be break, something we can represent like this. And here what will happen, here carbocation is there, and this is forming bond with oxygen like this oxygen is there. This is donating one lone pair to this one, we can see it like this is the transition state 2 and this is transition state 1, and here is the intermediate. Finally, the combination of nucleophile and carbocation will give rise to product like this. Then stereochemistry of SN1 reaction, we know that in like intermediate is carbocation. What is the geometry of carbocation? Suppose I can represent a carbocation like this. This is tertiary butyl carbocation. It is the geometry is trigonal planar. That means this whole molecule, it is present, this carbon, this carbon, this carbon, and this carbon, which is present on the plane of a board, we can tell. And if we add water molecule to this water molecule have two options. Either it can attack from front of board, or it can attack from behind the board, or below the plane you can call. That's why we will get a two option here, and that's why two molecules, that is racemic mixture. Racemic mixture we will get, and in chiral carbon we can explain the racemic mixture formation very easily. And here I am taking one chiral carbon molecule, which is methyl group is there, and here ethyl group, and in front case I will take hydrogen, and in the back side I will take bromine like this. Now when it get dissociate, it will give like carbocation like this, and here same ethyl group is there, and here H is there. Here is the positive charge. When the water molecule attack from top as well as the bottom side, we will get a two products, and I will be writing the two products. Okay, okay, here I will write, here carbon is there, and here methyl, and here ethyl group, here H is there in front towards the observer, and here I can write it as the away from the observer, and here OH like this. And the another molecule we will get it as exact mirror image of this. It is looking like mirror images of this like this. If we know the R and S configuration, we can assign the configuration to this. Suppose this is okay, I will write it as assigning R and S configuration. I will get it as 1, then here I am getting 2, and here I am getting this as 4, and this one as 3 like this. This one is like this it is coming, that means S is there. S will change to R. Suppose this is R configuration, if it is there, this is going to be S configuration. That means equal amount of R and S configuration is there. That means if R and S is equal amount, that means this is 50% is there and this one also 50%. Then we will call that mixture as racemic mixture. If you don't know about naming R and S configuration, it's okay. Just we can call it as, if we get one configuration, we will get a opposite of the equal amount. This is called as racemic mixture. Then, if we came to know what is the solvent we can use, we know that here a carbocation is forming as an intermediate. This carbocation has to, like, we can try to stable, like at least to certain time life it should have like that. Then we can use polar protic solvent. Polar protic solvent we can use, which can stabilize this carbocation till some time like that. Then if we, okay, now we just saw like proof for the carbocation. We just said carbocation will form. Then what is the proof for that? The proof we are getting by a famous scientist, Olha. His name is Olha. He prepared a tertiary butyl carbocation by treating, this is, suppose here I am taking tertiary butyl alcohol. Here I am taking tertiary butyl alcohol, plus to this I am adding hydrofluoric acid, HF. What will happen? This is acidic in nature. The lone pair is there. It will go and attack to this, and like this it will happen. And finally, what will happen? This, I will not writing 3-methyl group. Just like this I am writing, and here we will get a protonated alcohol, something like this. Then what will happen? It will leads to formation of carbocation like this. Carbocation. This is also Me, Me and Me. This is carbocation. When we observe in carbon NMR, we came to know that the chemical shift for this particular carbon, which is carrying a positive charge, it is going to be 320.6 ppm. This is the indication of formation of carbocation over here. For this methyl groups, the carbon NMR, the spectrum is delta C is 47.5 ppm. This indicates the proof for the formation of carbocation. This is high chemical shift is there, which indicates the formation of carbocation is confirmed. Now we'll see about, okay, rates of solvolysis of alkyl chlorides in 50% aqueous ethanol. Here we just used one term, a solvolysis. A solvolysis is nothing, SN1 reaction. What is substitution is happening over here? It is simply, we can call it as solvolysis. Solvolysis means the breakage of bond by this solvent molecule. Here in the example what we have discussed, I am taking a water molecule as a solvent. What is happening by water? The carbon and bromine linkage is breaking. That's why we can call it as hydrolysis in case of water, and in case of other solvent we can call it as solvolysis. Now here it is showing the compound name, and here relative rate is there, and here comments. Now you can observe the relative rate which is higher for this particular molecule, which is like this it is there, and here pi bond, and here chlorine, like this it is there. Now if this chlorine will move, then we will get Okay, I will now. I can write that particular carbocation over here like this. Here is the positive charge we are getting. Now what can happen? This pi bond is there, it can shift like this. We have to write this resonating structure and it will look this like this. It is there. Here we are getting a positive charge. This pi bond is there, it can delocalized from like over 3 carbon atom, and this is a tertiary carbocation which is going to be very stable. That's why we will get what the relative rate in the higher amount, and you can observe over here, right? This is going to be the least because it is normal primary carbocation will form over here. That is like this it will form, and there is no only inductive effect will work on this. There is no other possibility, and hyperconjugation will also work definitely for true like this hydrogen, and hyperconjugation will work on this. That's why this is primary chloride, whatever it is there, it is going to be very slow in case of SN1 reaction, and it is higher over here. This is tertiary carbocation will form as well as allylic carbocation. That's why it is going to be very stable. Now, carbocations are stabilized by adjacent. Before that, I will discuss this point. Why this tertiary carbocation is going to be very stable. You can observe over here, it is having a planar shape. You can one table is there. On table these three groups which is present on the table, and this is above the table one carbocation is there. This is empty orbital it is. Now what will happen, this carbon and hydrogen bond is there, it will show hyperconjugation. This CH bond, it will just overlap with the empty orbital. It is the effect of hyperconjugation. Hyperconjugation. Baker-Nathan effect also you can call, or sigma pi conjugation, or no bond resonance, whatever, one and the same it is. And you can see from other three also, this is only one orbital it is overlapping. Over here, three it can overlap. Total, how many resonating structure we can write it as? Total there are CH3, CH3, CH3. Total there are 9 plus this one. How many is there? 10 resonating structure. The more the resonating structure is there, the more the stability of carbocation. We can also suppose if instead of one this hydrogen, if suppose carbon is there, carbon CH3 group is there, extra stabilization we will get from carbon carbon sigma donation into empty p orbital of planar carbocation. But in case of primary methyl carbocation, we will not get such an effect. That's why this is going to be very stable and this is very unstable in nature. Now, we'll move on to the next thing, that is carbocations which are stabilized by adjacent lone pair. It will show a maximum tendency of showing SN1 reaction. Suppose I will take a simple molecule like this. Here oxygen is there and here methyl groups like this. Now what can happen? This is the carbon to which a chlorine is attached, correct? Chlorine is attached to this carbon atom, and here on the adjacent oxygen is there, oxygen have a lone pair. In such case what can happen, this lone pair will come like this and it will assist the leaving group to leave that particular molecule. Then what can happen over here? Here oxygen is there and it is forming a pi bond like this, and here simply CH2 molecule, CH2 group is there, and here it is attached to methyl. One lone pair is there and one positive charge is there. Now we can draw a resonating structure for this. This can come like this again. we will get it as oxygen, and here CH2, here we will get a positive charge, and here again two lone pairs is there, and here methyl group. Now what can happen? Any nucleophile we are going to add, it will attack this particular carbon atom which is giving rise to give product. Suppose if I take any alcohol ROH, I can represent, it can attack this carbon to form their own product. I will write, which is looking like here CH2 is there, and here oxygen, and here R group. R means any alkyl group, it can be there like this. Now I am taking any two example I am taking over here, just will solve and will end the session. Now you can observe over here the stable carbocation as an intermediate in SN1 reaction. A type of carbocation, it can be simple alkyl, one like types of carbocation involved in SN1 reaction. It can be simple alkyl like tertiary. It is going to be very good because we already saw that extra stabilization from carbon and hydrogen bond, hyperconjugation, it will work very good in case of this. And here it can be secondary is okay with SN1 as well as SN2, but it is not so good compared to tertiary, we can call. Then conjugated, if it is there, suppose we saw that the rate of a reaction is very high for allylic alcohol or benzylic, we can call. This is because of resonance effect, it will happen like this, and here like this it will happen. Then heteroatom stabilize. Now only we saw example of this one. This is, we can call the, if suppose a carbon which is having a heteroatom which contains a lone pair, this is going to be very good in case of SN1 reaction. Now we'll solve some problems. Okay, this is the first one and this is the second one. Now what was happening over here? We are giving tertiary butyl alcohol over here, and here potassium iodide is there, and here phosphoric acid is there. Acid means what? It will give H plus. H plus, what will happen? This whatever the lone pair is there, it will attack this proton. We will get something like this. Here hydrogen, one lone pair, one positive charge. Now what will happen? It will leave, water will leave as a living group, minus H2O, and we will get a carbocation like this, and Ki is there, which is the source for iodide ion. Iodide will attack this carbocation to give like this, tertiary butyl iodide as the product. Now here we are seeing two reactant. Here we are getting tertiary butyl alcohol. This is perchloric acid. This is the king of acid, correct? It will have a pKa of -10. Here it will give H plus proton, and same thing happen over here, and it will lead to formation of tertiary carbocation like this. And here we are getting this one as a nucleophile, and this whatever the sulfur belongs to oxygen family, it is also having two lone pairs. It will attack this carbocation to give, I will write the final product over here, it is like this. Here sulfur is there, after losing proton only two bonds will form, and here we are getting like this. This is the major product. We are getting this is as 93% and this product as 89%. I hope this video was very helpful for you people. Thank you very much for watching.